Yes, we are continuing our lectures on stability of structures, and today we will discuss a very simple topic, and that is, I hope we did not discuss that before, vibration of an all-round simply supported plate in presence of axial load. Did we discuss it before? No. Okay. So, if you remember, if we have just buckling, then this term is not present, this term. So this, okay, so that is actually, this term has to do with statics of plates. Statics. Now this has to do with buckling. And that, according to D'Alembert's principle, yes, according to the D'Alembert's principle, we are saying that we say d del del w plus p0 d2w dx squared. So that is what? Look, this has to do with the plate, and there is this load p0. P0. Now, if there was a transverse load, Qxy, so that is this transverse load Qxy. Okay, in this particular case, we have axial load and transverse load. Now, according to D'Alembert's principle, vibration equations of the structure can be obtained from the static equations by replacing the external load, external transverse load, by inertial term taken with minus sign. So this is a principle, and that means that it cannot be proved. D'Alembert just said, I, D'Alembert, tell you, the humankind, that is what you have to do. And up to now, we did not find that this principle was wrong. So this principle could be abandoned any time if we are finding just one example where it is wrong. So what he says that instead of Qxy, write down minus rho h d2w dt square. So that is what? That is m a ma equals f. So he says just instead of this load f, you put minus, because that is what how vibrations will be conducted. So therefore, if once we take this into account, we get immediately this equation. I transfer this minus rho h d2w dt square to the left-hand side, and I'm getting this expression. Now, for simplicity, we will put A equals B. So that means that this is a square plate. You can write down square plate. And then, I mean, later that we will see, and now I will still will carry probably B as I see here. So Wxyt is then thought, we are looking for capital A, which is an amplitude or magnitude, sine m pi x over a, sine n pi y over b, cosine omega t. Now we have to just write down here that that m is number of half waves in x direction, n is number of half waves in y direction, and omega is a natural frequency. Omega is a natural frequency. Now, we don't know the natural frequency, we are looking for it. Now, we substitute this expression into this differential equation, and we get del, that is Laplace operator, gives me m pi over a square plus n pi over b square with minus sign. But then I am applying again, I will get minus times minus, and we get plus m pi over a square plus n pi over b square squared, minus p0, here I'm getting minus p0, m pi over a squared, minus rho h omega squared. So from here we will immediately get omega, natural frequency, omega squared. But because this omega depends upon m and n, therefore it makes sense to give an index mn. Okay? Sometimes we want to magnify, that is like we put magnifying glasses. If you don't see something in the book or somewhere, then you like put a magnifying glass and you look what happens there. So omega sub mn. So there are many, many natural frequencies. Infinite, actually, because m goes from 1 to infinity, n goes from 1 to infinity. So it is infinite times infinity, so to say, a lot, natural frequencies. And that is this expression. Now I just put as follows. Look, please. P, there is this P0. P0 can be calculated, can be related as a fraction of critical load. P0 is gamma times P critical. Okay, so from here we get P0 equals gamma times P critical, and it equals gamma times. Now, for the square plate, we found this expression. 4 pi square d over b square. We already found previous time. So we get the following then. Look, I just repeat the first part. Then we have P0. Instead of P0, I put gamma times 4 pi square d over b square. And then there is divided by rho h. And then there is multiplied by m pi over a square. But I put instead of a, b. Okay? That is what we have. Now, what is gamma again? Gamma is a fraction of the buckling load. It means that gamma changes between 0 to 1. If P0 is 0, then gamma equals 0. If P0 equals P critical, then gamma equals 1. Now this can be actually rewritten as d over rho. There is d here and there is rho h. So here is d and there is rho h. So we could actually take out d over rho h. Okay? So d over rho h. And then this parenthesis, m pi over b square plus n pi over b square squared minus gamma 4 pi over b squared. And then there is m pi over b squared. Okay, so now what we do with this, it's very simple. You put m and n some numbers, and you can find omega 1, 1, omega 1, 2. So we can actually find here omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2, omega 2, 3, etc., omega 2, 17, etc. We can find all the natural frequencies. During the course on vibrations past semester, I explained to you what to do with this all large amount of natural frequencies, because we want to find the response. And response is written in terms of this infinite amount of natural frequencies. Now let us start. Naturally, I said that we can calculate omega 1, 1, omega 1, 17, omega 1, whatever. Now let us start with omega 1, 1. Let us start with omega 1, 1. So we get d over OH. Then we get here, look please, I'll show you. M equals 1, N equals 1. So we have pi square over b square. And then here we have pi square over b square. So these two terms are equal. So we get 2 pi square over b square. And that is squared. So we get 4 pi in fourth power over b in fourth power. Okay? Then it will be minus gamma. Now here we have also 4. Now m is 1. So here is pi square and pi square gives me pi in fourth power. B square and b square gives me b in fourth power. So we get actually the following formula. 4 pi square d over rho h b in fourth power times 1 minus gamma. So this is a linear relationship with respect to gamma. And that is this figure. Look, please. If gamma equals 0, then that means that p equals 0. P0 equals 0. So if gamma equals 0, then we get natural frequency without axial load. So this expression is natural frequency without axial load, natural frequency squared. So you may want to write down here like this. Natural frequency without axial load, and maybe like this, squared. Okay? So if there was no axial load, then that is what natural frequency would be. So therefore, when gamma equals, that is like gamma here. Gamma equals P0 over P critical. So when P0 equals 0, this is omega 1, 1 calculated for P0 equals 0. So that is this value. And it starts, that means, from this value and goes to 1. Because when gamma equals 1, we get 0. Now, that means that natural frequency vanishes when P0 equals P critical. So you may want to write down. Natural frequency vanishes, becomes 0, when P equals P0 equals P critical. Now, what does that mean? What is a period? Period is 2 pi over omega. Now, what is a period? Omega 1, 1 should be written there. Period is a time span in which system comes back to its original state. That is what period is. I mean, function repeats itself after this time t. Now, if function repeats itself after time t, but omega is in denominator, that means that when omega is 0, t is infinity. So that means that period is infinity. System comes back in infinite time. You may want to write it down. System comes back or returns to its original position in infinite time. So when two people tell each other, see you in infinite time, what does that mean? Mr. Andres, what does it mean when two people, one says to other, see you in infinite time? That means actually, that they never meet each other. So the system never comes back to the equilibrium position. Is it right? That is what buckling is. It leaves the equilibrium state, never comes back. Do you remember? That is what we talked. System suddenly gets deflection, another position. It was straight, and now it is not straight. And now vibration says, not only it is not straight, but it never comes back to this straight position. It stays there. Okay? So that means that natural frequency becomes 0 when axial load equals buckling load. Now, that actually allows us to do some non-destructive testing. Non-destructive test. Because what buckling is, if I want to find buckling load in an experiment, I just have to, look, how do? I will put some load, axial load, then I have to increase the load. And I'm increasing load, until system buckles. That means that until system actually goes from the straight position to a non-straight position. And then after that, this cannot be used. For just take, Coca-Cola can or any other can. I'm not propagating their name. So just buckle it, and you will pay attention that after that it does not come back to the original position, even if you put some drink inside. So that is called destructive test. Because we use this can, and then you cannot, that can change its position. It is a different entity now. Now, but we want to find P critical, if it is possible, without buckling. So we want non-destructive test, if it is possible. We always want to have non-destructive test, is it right? EKG, for example, is a non-destructive test. I mean, don't change anything in the body. Now, what we get now here is as follows. Look, please. Vibrate the plate. If that is the case, we can, by vibrations, can avoid buckling. What does that mean? We will vibrate the plate and measure the natural frequency. So, for example, first, do not put any axial load there. You will find natural frequency, which you will put here on this figure, here. Now, just increase this load, but don't bring it to buckling. Increase slightly this load, axial load. And at that load, just calculate the frequency. Okay? Then just pass the straight line between these 2 points, and then continue the straight line. Wherever the straight line will hit the horizontal axis, that is where the buckling load is. Because we established before that relationship was linear. So vibrations suddenly are coming to help the buckling case. Now, however, okay, that is what happens in these ideal systems. What I mean ideal systems, systems that have ideal shape. I talked about rectangular plate. Rectangular plate is an ideal shape of a plane surface. Now, however, this does not always happen. There is a paper of mine and my 2 colleagues in Journal of Applied Mechanics, 1984, a long time ago, 20 years ago almost. Okay, so there we show that relationship is not linear. Okay, for systems that is, okay, if you take a can and you already give it has a small imperfection. Take a Coca-Cola can. Now, this Coca-Cola can you may not observe, or beer can, or Coca-Cola can, or whatever. Now, why I talk about beer can? Because I spent a year or a year and a half in Netherlands, and there was this professor who would come to my office and would start the day by saying, I'm not a professor, I'm an artist. Okay, of course, as a rational person, I was very interested to know who he was, but he already gave me this information once. So he would continue and continue telling me this. And once I told him, you know what, because you're an artist and not actually a professor, as you told me, can you devise an apparatus that would measure initial imperfections of some shells? For example, beer cans, because I can contact, I told him, I can contact Heineken Company or Amstel companies and order from them beer cans. And you will make a device that will measure, because actually it looks like this, but actually the shape is like this. I mean, it is never straight. You don't see that actually. I mean, unless you will increase unbelievably the macroscopically, I mean, if you will measure out of roundness. So I thought that I will ask him this and I will never see him again. You know, that was actually my device, you know, to ask him to construct, as an artist, you know, some apparatus, because we already talked once about art and about Michelangelo and about other people, but so he went, and after, indeed, 2 weeks he did not come. But after 2 weeks, he brought actually, you know, many drawings, unbelievably beautifully done drawings. Then we went to the dean and we requested substantial amount of funds. And within 1 year, actually, this device was built. And we measured. We hired a student, and the student was very happy to measure beer cans, but beer cans were empty. You know, I phoned myself to Heineken and Amstel, and I was very kind to them. I tried to speak their language. I spoke Dutch, and when they heard my Dutch, they were so impressed that they decided to get rid of me and sent me as many hundreds of beer cans as I needed. And we measured, you know, these shells. And, for example, natural frequency, then theory was developed that I talked there. So natural frequency says omega 0, and that is, say, P critical. So That is if it was linear relationship. Because many people thought that because there is this linear relationship, they could do many things. Because if there is a line, then you just, it's very easy to draw a line. Even professors can draw a line. Not only the students. Now, it turns out that it does not behave like this. It behaves more like this. Non-linear. If there is imperfections, then it behaves more complex. And then you cannot just draw the lines, etc. Life is more complex. Life is more complex than it could seem. On the other hand, it is actually very simple. We can also say that life is simple, because if I know that that should be the relationship, then it is simple. It's only complex when you think that it behaves like this, and it is wrong. But if you think that it should behave like this, then actually life is simple. And the problem with these imperfections is, now I will not tell you, but Euler, of course, Euler did 1744. You remember this, yes? 1744, you have a good memory. Now, Euler, of course, considered straight beams, straight columns. But in approximately 1900s, people started to fly. So you cannot actually fly on a beam. That is not possible yet. Also, you cannot fly on a plate. Is it right? That is like a flying carpet. You have heard this. You have heard about flying carpets when you were much younger, if you remember. So it is necessary to have some shells. Rockets and satellites and, cosmonauts, astronauts, and taikonauts. That is a term now, new term in Chinese, taikonaut, which means space. That is what Chinese calls their astronauts. They need some shells. Now, these shells, as some professor said recently, these other shells behave as prima donnas. Today I actually learned about this. That is what one professor, Ram, says. Now, what does it mean they behave like prima donnas? What happens is that small imperfections have large influences. Small, what does that mean? Look, please. I'm taking a shell, and you better write all of this because it's important and your knowledge increases exponentially. I take a shell and I'm putting this under load P0. Now, what happened that this generalization to such shells occurred in approximately 1910. So Euler did his analysis in 1744. In 1910, approximately 3 people, Lorentz in Germany, Timoshenko in Russia, and Southwell in England, generalize this Euler's formula for the shell. These are three people. And since then, of course, Germans say that they were the first, and Russians say that they were the first, and English say that they were the first. And there is this priority problem. Okay? But most unfortunate situation is as follows. Look, please. You do calculations, theoretical calculations, p-critical theoretical. And that is experimental, p-critical experimental. So we divide one by the other and we get some, say, we want to plot this. That is radius over thickness. Radius over thickness. Where do you anticipate the points to fall? You anticipate points to be somewhere here, is it right? That is experiment and that is a theory. That is anticipation. Okay, that is experimental points. Somewhere there. They should fall around 1. Experimental value and theoretical value should be around 1 or a bit more or a bit less. But, there is a but. There is this 1, there is a straight line. They behave more like this. That is experiment. And this could be approximately 0.1. Can you imagine you design something for some load, but system buckles at 10 times less load? How to deal with this? How to deal with this situation? You have studied the strengths of materials, you have studied the design, you have heard some term that is designed for cases when you do mistakes in calculations. What is the name of that term? Safety factor. Question and answer of person 1, safety factor. But look, please, safety factor, actually I will put here question mark and exclamation mark, because how much safety factor will you take? 2? If you take safety factor 2 is not helpful, because theoretical value say is something, you divide it by 2, but in experiment it buckles 10 times less. So no one is going to take a safety factor of 10 or 15 or something like that. So safety factor is not helpful. Because safety factor, I mean, unless you will, can you imagine if you would do calculations by finite element method or analytically by using Bessel functions and Lommel functions and convergences, etc., and you would do calculations, and you would do, for example, stress would be, for example, 17, 5, 2, 3, 7, 0, 9, 4, 5, 7, 6, 0, 3, 2. So that is from computer, of course, yes? Computer gives a lot of numbers. So that is the stress. But if I have to divide it by 10, why in the world I need so many, these things? Who needs this? If I have to divide it by 10 after that. If I am uncertain 10 times, so who needs this so much calculations? That is nonsense. Okay, that would be a nonsensical calculation. So what is necessary to do is to incorporate the initial imperfections in your theory. Okay, that was done in 1945, before most of you were born, I think, I suspect, but I'm not sure. by Warner Tiardus Koiter. Okay, he's born 1914, 1997. So Koiter developed a theory that takes into account initial imperfections. We will come back in the future, hopefully, to these initial imperfections. Now we would go to something that was given to you as a homework, but before, in order not to leave you, because I use this word homework, I don't want to leave you homework-less. So I will assign you a homework. Homework will be not difficult, actually not very difficult at least, but you please use Maple and or Mathematica. Now, why I said and or, what should I have said, Mr. Plasencia? What should I have said, Ms. Gentilini? I should have said or. Okay, why did I say and or? But I said what I said. I said and or. Why? Mr. Gomez, can you guess? No. Mr. Penteras. Mr. Berezhnoi. Say it again? Spontaneous mistake. I just hand wrote it. I mean, I did not control my hand when I wrote it. That was your suggestion. Okay, that is a good suggestion. But can you give me more plausible explanation? Mr. Plasencia. Speak louder. Why do you, okay, Plasencia. Do both, compare them. Okay, that is a good guess. But why should I do both? I mean, do you get double lifetime if you do both? Or I mean, do you have a guarantee that okay, you spend time, but it will be added to your lifetime at the end? Why should we do double? For example, if I have problem to solve, do I have to solve it by finite element method and then finite difference method, and then by Galerkin and then by Ritz? Mr. Andres, I think we did not disturb you, and Miss Santoro. Don't sit so far, I don't see very well. Miss Santoro, what could be a reason?
Sometimes it's, we need to have a confirm of results.
Okay. Yes, Miss Santoro says, so I'm not going to disturb you anymore because she said everything. Miss Santoro says, sometimes we need to confirm the results. What does it mean to confirm? Because unfortunately, that is an ugly fact. Sometimes give different results. Because they could have different inference engines. What is a better word, more colorful word for inference engine? Like humans have different what? Characters, what else? They have different brains. Okay, in this case. Because look, Those who developed Maple used one system of derivations that is not just the same. And the others used other types of derivations or other analytical approaches. And most unfortunately, we just, I have a student who is doing master's thesis with me. So he has nothing to do, so he decided, I don't know why, to solve the same problem by Maple and by Mathematica. Actually, it's very simple. I'm just exaggerating. He had a program with Maple. Then suddenly he got an offer on Mathematica he could not refuse. It was very cheap. So he decided also to buy Mathematica. Now he found himself very rich man having both Maple and Mathematica. Now he had already results on Maple, and now he obtained the results with this new fast Mathematica. And he obtained different results. So he got stunned, and when person is stunned, he comes to me, because they like also me to be stunned. So we found that that is a different engine. There are different brains there. So that means that you cannot just, say, Maple, now solve my problem. Or Mathematica, please now solve my problem. You have to check back, does the solution that you got, does it satisfy everything? Does it satisfy boundary conditions? Does it satisfy a differential equation? What would happen if I would do it by Mathematica or by Maple, etc.? That is if you are extremely conscientious a person. Naturally, for homework in the stability course, we are not building anything, so to say. Maybe one approach would be sufficient, but therefore, and or, however, I said means that or use Maple or Mathematica, or use both if you are an extremely dedicated person. But paying attention that I did not describe a problem yet. I'm just talking about how to solve it. Now, problem is very simple. You remember this problem. So you had this homework to generalize semi-inverse problem. So d of x is a function of e of x, I of x, yes? So that is a flexural rigidity. Now this flexural rigidity is variable. Now, what did I write here? Now we have, and what you have to do, if you remember in one of the homeworks, to find, first of all, clamped free beams as a fourth order polynomial. That is a mode shape. That is, say, psi of x equals a0 plus a1x plus a2x squared plus a3x cubed plus a4x4. Then you satisfy boundary conditions. Psi at 0 equals psi prime at 0 equals 0. And boundary conditions here will be psi double prime equals 0, and then d times psi, that is a moment, time first derivative, that is a shearing force, plus p psi prime equals 0. Now that you already had this problem. You already had this problem. We wanted to find d of x so that this psi is the exact buckling load, buckling mode. So what we are saying actually is as follows. So this is a beam. Then that will be this, that will be and we say, hey beam or column, you must have the buckling load, buckling mode that I, and then you put your name here, decide. You are telling the column how it should behave. You become suddenly a boss of the column. Now the only difference from that problem is that this has also this load, distributed load also. Q sub 0. By the way, this is a simple problem. Don't get excited or don't get frightened or something like that. That is a simple problem for intelligent people like we have here. And everyone is very good, extremely good. So if you can afford it, I mean, if you have Mathematica, then do it in Mathematica and then Maple. But not everyone, of course, who has Mathematica. Maple is available in a FAU, yes, in our, who has Mathematica? One person. Does anyone else have Mathematica? Huh? You also have. Now, maybe someone has MATLAB. Who has MATLAB? Okay, the rest can use MATLAB. So you are just one program person? Okay, then you do that on that one program. So we have only one person, two actually, I'm also in between them, two people who have just one program, but the rest, but I ordered the Mathematica that you are using. Okay, so that is a homework. Now, by the way, I'm not opposing that you cooperate with each other. Say two people. We have what? Odd number of people, yes? So on one, if you want, so 3 people can get together, and in other case, only 2 people. So 2, 2, and 3. Or 2, 2, 2, and 1. Okay, if you are uncooperative, then you can stay by yourself. Okay? What else? Here there will be just one problem. I mean, what I'm asking you is as follows. Look, please. There will be a question, what is a buckling load? What is the buckling load? So before that, when we had Q, when we have Q only, that means that there is no P, and then we found Q critical. If we have P only, then no Q, and we found P critical. What are we looking now? That is a question. An answer is very simple. So there is some proportionality. Q times L has the same dimension as P. So we can think about, look, following scenario. P equals gamma times QL. Gamma is fixed. And then we are looking for Q critical. Or we can look differently. Q equals alpha times P over L. And we look for P critical. So you can substitute P equals QL, gamma QL, and then you have just one parameter Q. Gamma is fixed. By the way, why do I talk about cooperation? It is not because naturally it is much easier to solve the problem. when you are two people put their heads together. But even more important is that you are not just, this is not a division of power, so to say, like physical power. Let us say if we have to transfer 1,000 bricks, then one will transfer 500 and the other will transfer 500 bricks. And then that is factor of 2 appears, 2 times easier. But here you are, that is a mathematical problem, you are talking to each other. So suddenly this interaction of talking reduces this factor of doing by factor much more than 2. It's not just transferring bricks. You are also discussing the problem. So that process of thinking is reduced maybe 7 times or 5 times, or etc. Therefore, it is good to be competitive but cooperative. So that is, it is opposite properties, but it is good to combine both, cooperation and competition of sorts. Okay, any questions? Now we go to the problem of circular plates. Okay, and that is given here actually in the book by Timoshenko. So what happens at the circular plate, you have actually these pages. We requested that Mr. Andres would send to you the material by electronic mail. So each of you has this material. Now, what happens is that in this particular case, we talk about axisymmetric buckling. So, look please. We had, say, in the plate buckling, say, we had d del del w plus p0 d2w dx squared equals 0, yes? So del was operator d2 dx squared plus d2 dy squared. Now, if we talk about d equals constant, then we can actually say we want to write delta in polar coordinates. Now, what is a polar coordinate system? So this point, so the distance from, this is radius. Radius is A, as Timoshenko denotes, A, radius of this. Now this point, so this distance is small r. And this one, this angle is theta. He does not give this, theta. So actually Laplace operator then is written as d2 dr squared plus 1 over r d dr plus 1 over r squared d2 d theta squared. That is how Laplace operator is written in polar coordinate system. That is not written now here in this book. Now w is a function that means of r and theta. If w is not a function independent of theta, we talk about axisymmetric vibration, axisymmetric buckling. Axisymmetric buckling means that if I look here, then it looks like this. And that means that in any theta direction, we see the same picture. Okay, that is here. In any direction, we see this picture. If I look from here, if I look, that is an eye, I will look at this diameter, and picture is like this. So it does not depend upon theta. Then delta equals d2 dr square plus 1 over r ddr. Because dependence with respect to theta disappears. W is not a function of theta. Therefore, when you differentiate with respect to theta, we get 0. There is nothing there. There is no contribution. And partial derivatives are changed into direct derivatives. Okay? Now, actually, Timoshenko derives the following differential equation. Now, he introduces not W, but new variable dW dr, which is a slope. Slope in radial direction. And this, you may want to write this because it's not written here. And this is, he denotes as phi, or phi. This phi is dW dr. Why does he introduce this? Because the order of differential equation will be easier, is it right? Order will be not force order, now will be less. So what he writes actually is as follows. dr square d2 phi dr square plus r d phi dr minus phi equals, and then he says minus q r square over d. Now, what is this Q? Q actually is QR, like. That is a shear force in R direction. And what he shows actually here, maybe I don't have to draw this picture. Yeah, you may want to draw just separately this picture. This is actually a shearing force. That is an element. This is a small element. Please increase it. The small element on the left-hand side, Q, is up, and on the right-hand side is down. And then naturally, look, this is this element. Where should I move it? Oh, it's here. That is this element. So here that is this, but there is also this force, is it right? This is NR. That is this axial load. That is Q. So if I consider the equilibrium in this direction, equilibrium in this direction, I will get Q, okay? And then this NR is multiplied by this angle. And we get nr times phi. Because tangents phi equals sine phi and equals phi approximately. Now, if that is the case, now we substitute this back into the differential equations, is QR. QR is connected with nr and phi. So we get r squared, let us write down phi second derivative, plus r phi first derivative, minus phi. Then it equals minus q, which is nr phi d and r squared. This could be transferred now here. And we get r squared phi second derivative plus r phi first derivative plus, and then we have nr over d r squared minus 1, and that is phi equals 0. I transferred this here and took out phi. Now he denotes nr over d as some alpha squared. Then we will have here alpha squared r squared minus 1. Yes, so I will rewrite down. R squared phi second derivative plus r phi first derivative plus alpha squared r squared minus 1 phi equals 0. Now, because I have alpha squared r squared, I would like to get rid of this alpha squared r squared and have just one quantity, so I can introduce alpha r equals u. Because alpha r is a non-dimensional quantity anyways, as I see, because alpha squared r squared minus 1, it says. So then we get, look please, d phi dr equals d phi du dr. This equals d phi du, and du dr equals alpha from here. So that means that d2 phi dr square equals d2 phi du square alpha squared. Yeah, because if I will do once, I will differentiate this once, I will get alpha. So now I will get 2 alphas. So that is this term. So the first term will be r square d2 phi dr square will be equal r square alpha square d2 phi du square. But this is u squared. Neat, yes? That is what we got here. Now, that is the first term. Second term, we have r phi prime. So r d phi dr. But d phi dr equals this. D phi dr equals d phi du alpha. This equals r alpha d phi du. R alpha equals u d phi du. Now this term, there is alpha squared r squared, but this equals u squared. So we get u squared d2 phi du squared plus u d phi du plus u squared minus 1 phi equals 0. Okay, this maybe we recognize better like this. We divide by u square. d2 phi du square plus 1 over u d phi du plus 1 minus 1 over u squared phi equals 0. What equation is that, Mr. Berezhnoi? This equation has a name. Okay, another person who lectured about this is Mr. Andres. Whose equation is this? Bessel. Okay, no problem, you just forgot. So this is a Bessel equation. That is why we need Bessel equation. It is not that we just like Bessels or something like that. We just need them. So that is this equation. So solution then is written in terms of this one. Phi equals a1 j1 of u plus a2 y1 of u. You remember I asked someone to have the second function of the Bessel functions. That is why we need it. First function was given by Mr. Andres, and second function by Mr. Berezhnoi. So this is two Bessel functions that we have here. That is a second order differential equation, and we have two Bessel functions as a solution. Now, J1 and Y1 are Bessel functions of first order, of the first kind and then second kind, respectively. Now, at r equals 0, the angle must be 0 in order to satisfy the condition of symmetry. If the derivative is not 0 there, look please, we said that it is a symmetric behavior. Symmetric behavior means that with respect to this line, there is no preference to the left or no preference to the right. That means that solution should be like this. That means the derivative must be 0. Symmetry demands that first derivative of function phi in the middle must be 0. Otherwise there is no symmetry. Otherwise it would be like this, for example. It could be like this, but then it is not symmetric. Okay, so that is not allowable. Now, he measures also the coordinate system from the beginning, from the center. So at the center of the plate, r equals u equals 0, there should be a symmetry. That means that now Bessel function at 0, we have certain behavior, but this second kind Bessel functions becomes infinite at 0. So therefore, this function that is infinite, becomes infinity at 0, cannot participate in the game. Therefore, A2 must be put 0. I mean that we should discard that because it does not answer our physics condition. Displacement, I mean, the slope cannot take infinite value in the, this plate has a finite value of the slope. Not only finite, it should be 0. so that A2 must be 0. Because A2 must be 0, this function does not play a role, which is very good news for us, because we actually did not have a lecture about this function. But no problem, this constant in front of it is 0, so it's okay. Now, what happens is as follows. We consider now the clamped end. If it is a clamped end, then first derivative of w, or phi in this case, must be 0. That means that Bessel function calculated at u equals alpha a, remember u equals alpha r, but r equals a, alpha a must be 0. Now, smallest root, I would like to ask Mr. Andres to send everyone the program of calculating the Bessel function. But you took, how many terms did you take in your calculation? 6, I thought? 7. So can you but you don't care about how many terms. Yes, you can put 20 also, or 50 or whatever. So write down 100 terms. We should be large, you know, because that is computer is doing anyways calculations. We are not doing it, so we don't care about number of terms. Take 100 terms. Okay, and once we have this function, say we can find. Okay, in this particular case, what look please what professor of course, late Professor Timoshenko says. He says the root equals 3.832. How did he find the root? I will tell you. He has a book, Janke and Emde. I even have this book translated into Russian. I mean, but these books already should be probably exhibited in the museum. Now, this book is called Tables of Functions. So can you imagine page after page after page after page, you have tables and numbers there. So including some pages are Bessel functions. And what you are doing is you start looking at this page, and if the sign does not change, then you go to the other page. And you look where this Bessel function changes the sign. When you see that Bessel function changes the sign, that means that at that argument, there is 0. This function has 0. And that is how Timoshenko, by looking in the book, found the roots. We, of course, are asking His Excellency the computer to find the roots. Is it right? And computer gives many numbers. Okay, so we have just 1 second left. So that is a root. If that is a root, then we get critical load, which is 3.832 squared d over a equals 1468 d over a squared. Okay, so when this load, compressive load, equals 14 times 68 times d over radius squared, then this buckling occurs. Next time, I will demonstrate to you that also for plates we can use semi-inverse method that I devised. We can have inhomogeneous circular plates and get very simple solutions in just a few minutes. Thank you very much.